welcome to CERN, welcome to this fantastic open day, welcome to the Hadron Cafe, and a big welcome to Professor Bernodz, Nobel Prize winner 1987 for his work on high-temperature superconductors. Today, he's very kindly come and agreed to talk to us about his work on high-temperature superconductors, and there will be also an opportunity for you to ask some questions a little bit later on. Yes, big round of applause. Thank you very much. Professor Bernodz, high-temperature superconductivity, what is this?
Is the phenomenon of material losing all its resistance at a defined temperature. And we call the temperature where we observe this transition high, although it's still low. Today, in the new materials we discovered, it's minus 150 degrees centigrade. But it's high as compared to the temperatures used at CERN today to obtain superconductivity. That's not, close to the absolute zero, which is needed to be reached. For cooling the magnets you have the opportunity to see today to obtain the superconducting state.
In 1987, I believe CERN was already designing the LHC. Could they have possibly considered using your style, high-temperature conductivity superconductor?
Yeah, I have to say that at CERN there was a little concern about the new development which we initiated. The plan was to use these low-temperature superconductors for winding these magnets used to bend the particles in the ring. But they also were concerned that the new material would be another choice. But I would say it was a right decision which people made during these times at 1986-87 to stick to the old materials, because the development of the new superconductors, which are a completely different material, never experienced before, the development took a long time.
Okay. When you were looking for these new materials, were you looking in the dark, or did you have some clue as to what you might find or where you might look?
We were looking at oxide materials. Oxides were not considered to be good conductors during these days. But we had some signs, and we had some hope that we would find the phenomenon of superconductivity at elevated temperatures. But there was no theory. So we never were sure whether we were following the right direction. But with a bit of luck, we ended up, after 3 years of research, in the discovery which turned the superconducting world around.
And today, is there any hope, is there any chance that we might have superconducting materials that will operate at room temperature?
Well, let me see. Let me first refer to CERN and the use of superconductors, of high TC superconductors. In parts of the system of the Large Hadron Collider, the new superconductors are already engaged. Now, your question concerning room temperature superconductors. For that, we have to know why these oxides, for instance, are superconducting and not superconducting at room temperature. When we understand the physics behind the new high TC superconductors, we eventually will learn more to hopefully discover new materials which might superconduct at room temperature.
And are you still working on this problem?
I have to admit I skipped that topic many years ago, and I'm presently working again on insulators, oxides, which get conducting if they are exposed to an electric field, to a strong electric field. Conducting but not superconducting. But they are very useful probably for constructing a new computer memory.
Thank you. Now we're going to move over for a few minutes to some exciting experiments that are going to be shown to us by Physica Express. We're going to have some hands-on, so focus over there now for a few minutes. We'll come back to Professor Bernodz in about 10 minutes. So if you have some questions that you would like to ask him, think of them now, and you will have 5 minutes near the end, okay? So, Physica Express.
Hello, we're Physica Express from Croatia. This is Carlo and I'm Ivan, and we're going to show you some things about pressure and vacuum. And we have here what we call our vacuum bazooka. And we call it bazooka because it actually it does what bazooka does. It launches a projectile, which is this cork. And we have this down there, a vacuum pump, which is going to pump out the air from inside this tube. So let's see. Okay. Okay. We'll turn it on and just a minute.
These young people have come all the way from Croatia, from the University of Zagreb, to be with us today.
We have some little bit of technical problems.
Technical problems.
Okay, too much problem with that. We'll come back to that later.
This is real science.
Yeah, you never know what's going to happen.
Never works the first time, okay? I'm sure Professor Bernodz can give you lots of stories about things like this.
Sorry about that. We're going to put a balloon inside this vacuum chamber and pump out the air. And hopefully this will work. And you'll see what is going to happen to the balloon. Okay. We plug it in. So what we're doing, we're creating vacuum inside this chamber. And as you can see, the balloon is starting to grow. The reason it grows is because you have one pressure inside that balloon and the other inside this vacuum chamber. And we're making it smaller and smaller. And because of that, we have a pressure that pushes the balloon to expand. Because you have greater pressure inside the balloon than in this atmosphere. And if we pump up the air inside, the balloon will shrink. Okay.
Bravo, big round of applause. Are you going to try your cannon again?
Okay.
You're going to try again. Physicists never give up. Hey, bravo. Well done. Thank you very much. Physica Express all the way from Zagreb. Big round of applause for them, please. Thank you. And now it's time to hear some more music from Home Cooking.
Sherlock Holmes, Charlie Chan, and his number one son put the finger on me, but I don't know what I've done. This guilty conscience could not be man, 'cause it feels like someone else all the time. Blue lights flashing and the sirens call. I'm in the spotlight, but I'm not really here at all. I'm just standing at the scene of the crime, and it feels like someplace else all the time. It's a case of mistaken ID. I'm a mugshot of innocence. It's just somebody who looks like me in any way. It was self-defense. Now I'm a desperate man, and I'm on the run, like Colonel Mustard in a greenhouse with a smoking gun. One step backwards over the line and gets you someplace else every time. Blue lights flashing and the sirens wail. You pick a card, any card, and it says go to jail. I'm made for the border, but I don't get far, 'cause it feels like someone else in a getaway car. And it's a case of mistaken ID, circumstantial evidence. It's just somebody who looks like me in any way. It was self-defense. So jailer, jailer, bring me water. I was the lookout man, but I didn't see what I oughta. These bad dreams always end the same, up on the grassy knoll, taking careful aim. And it's a case of mistaken ID. I'm a mugshot of innocence. It's just somebody who looks like me in any way. It was self-defense.
Thank you, Home Cooking. Big round of applause. I've always actually wondered where the name comes from, but he doesn't have a microphone there. Oh, yes, he does. Where does it come from?
There used to be more of me.
Okay, thank you. Just a little advertisement. If you want to know more about superconductivity, then of course there are many things you can look at around the laboratory today, but there is also a lecture this afternoon at 2:30 in the main amphitheatre of CERN. That's near the main restaurant, and Professor Bernodz will be talking. What will you be talking about, please?
I will be talking about the discovery of this new class of materials and the impact on technological applications, and applications which are already very close, like transmission of power, like magnets application, and biomagnetism.
This lecture will be translated in real time, by the way, or interpreted in real time into French. So, I have a question for Professor Bernodz. Will you be following with interest what's going on at the LHC over the next couple of years?
Certainly, yes, because I see a potential also for the application of high-temperature superconductivity and the great experiments which are running very soon are of great interest for the whole world. And so I started to dig into your internet, and got a lot of information which I enjoyed very much, especially the talks and the educational value of these talks.
Thank you. And of course you can do the same, www.cern.ch, and you can find exactly what Professor Bernodz has found. Now it's your turn. Does anybody have any question to pose? Don't be frightened. You can do it in French if you wish. No problem. I will translate. Yes, there's a gentleman sitting over there with his hand in there. Could you stand up? So we have a little guy who's running around with the microphone and he can't see over the heads of people. Kieran.
Hi there. My question is that when you achieve these very low temperatures near absolute zero, did you find that there was a residual field that you weren't expecting that existed near absolute zero?
There might be a misunderstanding. We didn't go to absolute zero with our compounds because we were looking at temperatures far above. So we never were worried about residual fields in that sense because we were hunting for higher TCs.
What is the highest temperature superconducting material
So that temperature has been reached many years ago. I remember correctly in 1993 by researchers at the ETH in Zurich, and the temperature was 135 Kelvin, that's minus 140 Celsius roughly. The nice thing with the superconductors, and this might a clue for learning more about that, is that if you apply a hydrostatic pressure to these compounds, the TC goes up even more.
The TC is the
critical temperature, the transition temperature from the normal to the superconducting state goes up even more. And in that particular compound, it was 165 Kelvin, so more than 30 Kelvin up.
Okay, thank you. You have a question. Physica Express has a question.
When you performed your work, your experiments in discovering high temperature superconductors, you obviously coming across to much of doubt from your colleagues. So basically, for what I heard, that people didn't believe that it's possible. So I was wondering, what was your driving force? What made you go on with your research?
My own persistence. But you were talking about doubts. During the whole 3 years, we didn't talk, my colleague Alex Müller and myself, we were two persons involved. We didn't talk to anybody about our project because we were afraid that people would consider these plans as totally absurd. So it was a secret between the two of us. Only when we had the first results, we were trying to get colleagues involved. Nevertheless, these colleagues, specialists in superconductivity, in low-temperature superconductors, these colleagues had severe concern that we would make a misinterpretation, which finally turned out to be not true. So what we measured was so convincing. We had first to convince ourselves, and then the rest of the world.
Thank you. Another question?
How can students or people who want to learn more become more involved in experiments like this?
You need to make the proper choice for the proper professor who has the right attitude. Now, let me make a citation of somebody who I admire very much. It's a chemist, and he is somehow representative for the spirit of those works which lead to a breakthrough. He said, big breakthroughs are made by those who regard nothing as impossible. And if you have this attitude, first of all say, why shouldn't it be possible? Why do I have to stick to these rules? Then you probably end up having a very successful research career.
So choose yourself a good teacher and don't believe what they say. What has winning the Nobel Prize meant for you?
A situation where you find yourself being admired by a big public, and this big public is expecting you to be an expert in all areas of science, for instance, which is not true. This is a burden. But there's also some very nice events that you are open, doors are open for you to visit very interesting places, like for instance today here at CERN, which I never made it to, and I thank you, the organizers for of this important day, this open day, that I have the opportunity to get at least a certain glimpse.
Thank you. I asked Professor Bernodz if he would have time today to go around and have a look at our installations, and unfortunately his program is very heavy, but he has asked if he can come back and look like you. And of course the answer is a very big yes, and we'll be delighted to invite him back and show him around sometime in the future. Is there any last question from somebody, please? Yes, gentleman over there, Kieran, if you have to run, go. Okay, I go.
Just to understand a little bit more about absolute zero, does it actually exist? Has it existed? And just share more information about it, or is it a more theoretical concept?
So in theory, it exists, and the technology is making very, very good progress in approaching that absolute zero. The technology nowadays is, as far as I remember, is in the range of a few millikelvin or even microkelvin, very close to this absolute zero.
So that ends this session of the Hadron Cafe. Thank you all very much for coming to visit us today at CERN. I hope you have a tremendous day. I hope you find it interesting and useful. Big round of applause to our very, very special guest today, Professor Bernodz. Thank you. Thank you to Physica Express. Thank you to Home Cooking.